have a look at a specific example. So remember this rule, go with the arrow, keep the sign the same, go against the arrow, you change the sign. So we're going to calculate the enthalpy of formation of pentane from their elements and their standard states. So we've got obviously our enthalpy of combustion data, so we know it's a combustion cycle. Here's our elements and their standard states, there's pentane and oxygen. So the first bit we need to do is write our combustion products, make sure they balance, 5 carbon dioxide, 6 waters, and we're going to use this information here to fill in the cycle. So we've got 5 lots of carbon, which is minus 394, it's minus 1970. We have a H2, we've got 6 lots of H2, so there it is there, so it's minus 286, so it's minus 1716. So the total for this side, remember oxygen we don't count, in fact we can cancel oxygen out left and right, because obviously we've got oxygen on the right and on the left, so we just ignore that. So enthalpy of combustion is minus 3686. Let's look on the other side now. Enthalpy of combustion of your pentane is minus 3509. We only have one of them, so that's fine. The oxygen we can ignore, so the total is minus 3509. We can ignore it again because we can cancel them out there.
We need to locate a bomb.
We want to work out the enthalpy of formation, which is this bit here. Again, when we're doing the cycle, we need to go from here to here. Imagine that's a roadblock, so we can't do it. So we're going with the arrow here and against the arrow here, so taking that diversion. So with A means minus 3686, and against B is plus 3509, equals minus 177 kilojoules per mole. So this is basically the enthalpy of formation of pentane, minus 177. So this is an excellent reaction. Okay, again, put your numbers in, start anywhere on this cycle, with the arrow changes to keep the sign the same, against the arrow change the sign, add it all up, should add up to 0.
Reloading ammo.
And that is it. That is basically an overview of the enthalpy changes part that you need to know for OCR-A. Please support this channel by subscribing to it. If you just click on that circle there, and you keep up to date with all the new videos that we put on. And just remember that if you want to purchase this slides, if you like the look of it, then if you just click on the link in the description box below this video, and you can get access to it there. So that's it now. Bye bye. Hello and welcome to this video on enthalpy changes. This is for OCR-A. My name is Chris Harris and I'm from allerytube.com, and basically we're just going to go through the enthalpy changes topic as part of OCR-A, like I say. These slides that we're using here are available to purchase. If you just click on the link below in the description box, you'll be able to get them from there. Okay, so yeah, like I say, this video is specifically for OCR-A to meet the specification points that are on display now. Okay, so we're going to look at enthalpy first. We're going to say what is enthalpy. So when a chemical reaction occurs, there's normally a change in energy. Okay, so the enthalpy change of a reaction is the heat change in a reaction at a constant pressure. Okay, so that's what we're looking at. So it's given the symbol delta H and kilojoules per mole, or kJ to the minus 1. And it's given this here, which is a triangle. It just means delta, it means change. So basically we're looking at the change in enthalpy. And the little underground symbol here, this means under standard conditions. Standard conditions. So everything is basically kept constant, so we can compare them. And the standard conditions are 100 kilopascals of pressure and 298 Kelvin or 25 degrees Celsius. Okay, so let's look at exothermic and endothermic reactions. So reactions can give out heat energy or take it in. So endothermic reactions, these are reactions that absorb energy from the surroundings. So for example, the products in this reaction are higher in energy than the reactants, and delta H is positive. So you can see here, there's the energy required to move from reactants to products. Products are higher in energy, so this is an endothermic reaction. Energy is taken in to produce your products. Okay, And you can see here that we've got an activation energy as well. This is the energy profile of the reaction. And so basically this bit from the reactants to the top of this energy profile is called the activation energy. We'll look at that in a little bit more detail. So an example of an endothermic reaction is calcium carbonate, decomposition of calcium carbonate. You'd form calcium oxide and carbon dioxide, and obviously the enthalpy change of combustion, in this case, is endothermic, plus 178 kilojoules per mole. Okay. Exothermic reactions, these are the opposite. These release energy to the surroundings. So your energy profile diagram is basically looks like this. So your reactants are higher in energy than your products. Energy is released, so it's delta H is negative because our products are lower in energy than our reactants. And there's our energy profile, our diagram. Again, reactants to the top of this energy profile here. We'll go into activation energy later. But basically, green arrow the activation energy on this energy profile. An example of an exothermic reaction is ethane, burning it, which is combustion of ethane, and we produce water and carbon dioxide, and this is enthalpy of combustion because we're burning it again. So this is going to be minus 1560. Obviously, we're burning a fuel, so it's going to be exothermic. We're going to produce heat. Okay, so know your delta H's. Okay, there's 4 types of enthalpy change that you need to know. You've got enthalpy change of reaction with a little r there, so delta RH with the little underground symbol. The enthalpy change of reaction according to the molar quantities in the equation under standard conditions. Okay, so this is just the standard reaction. Delta Newt H with the underground symbols is theta. I should stop calling it out really. It's the standard enthalpy change of neutralization. So this is basically the enthalpy change when an acid and alkali react to form 1 mole of water under standard conditions. Very, very important. Okay, make sure you know these definitions. The next one, standard enthalpy change of combustion. So this is the enthalpy change when 1 mole of a substance is completely burnt in oxygen to make carbon dioxide and water under standard conditions. So all of these are gases basically. So make sure you know these definitions. They're so important. It's completely burned, 1 mole of substance is completely burnt. And the final definition you need to know is the standard enthalpy change of formation. This is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. Okay, so you'll see these being played out later on in the video. Okay, so bond breaking and making. So bonds are broken and made during a reaction. Obviously, when we react to these things, we have to break some bonds. So bonds are broken. Energy is needed to break bonds, so energy is actually absorbed. And because energy is needed, this is an endothermic process. So delta H is going to be positive. So let's go back to this energy diagram again. You can see delta H. More energy, if more energy will break bonds than energy given out to the bond, or produce products, overall the reaction will be endothermic. And let's look at bonds made. So this is when bonds are formed, energy is released. So obviously, because it's an exothermic process, delta H is going to be negative.